Hi, and welcome to day 5 of exponents. So today we're going to be talking about exponential growth and decay functions and their graphs. An exponential function has the form of y equals ab to the x, where a is not 0, the base b is a positive real number other than 1. If a is greater than 1 and b is greater than 1, then, if a is greater than 0 and b is greater than 1, then y equals a times b to the x is an exponential growth function, and b is called the growth factor. The simplest style of an exponential growth function has the form y equals b to the x. Some important things to notice about the graph is the fact that, 1, so the first thing is the graph rises from left to right while passing through the points 0, 1 and 1, b, whatever the base is. And I've located those 2 points on your graph. 2, the x-axis is an asymptote of the graph. Okay, so that means that the graph is going to get really close to x. X is right here, but not ever really touch it. The domain of this function, my x values, I have no restrictions on them. So the domain of f of x equals b to the x would be all real numbers. And we're talking about the domain, might as well talk about the range. So the range is, if you notice, I don't go below the x-axis, therefore I don't have any negative y values, and I don't touch the x-axis, so therefore y has to be greater than 0. All right, moving on. If a is greater than 0 and b is between 0 and 1, then the graph y equals a b to the x is an exponential decay function, and b is called the decay factor, so the growth factor. So 1, the graph falls from left to right and passes through the points 0, 1 and 1, b. The only thing that's different from up above is the fact that this one falls where the other one rises. So decay is falling and growth is rising. Or decay is decreasing and growth is increasing. The second thing is the x-axis is the asymptote of the graph. And that's exactly the same as it was in the graph up above. So our domain here of f of x equals b to the x is still real numbers. I should probably say all real numbers. And my range is still y is greater than 0. Now, this doesn't change because the actual format of the equation is the same. The only thing that's changing is b is becoming a number between 0 and 1, so it's a fraction. Okay, so now we're actually going to graph. First thing we need to do is tell whether each function represents exponential growth or exponential decay, and then graph the function. So our first graph here, y equals 2 to the x. My base is equal to 2. Ooh, dear. Hang on. Okay. Sorry, my base is 2. Therefore, this would be considered growth because it's greater than 1. On my graph, what I'm going to do is put it into y1 in my calculator. And I'm going to pick some points, write down my table. And when I do that, I get these lovely values. So negative 2, 1/4, negative 1, 1/2, 0, 1, 1, 2, 2, 4, 3, 8. And if I go ahead and plot those points on my graph, I want you to notice the scaling. Not every line is 1. So notice the scaling of the graph. Careful. So at negative 2, each mark is a half. So at negative 2, I'm at a quarter, I'd have a point down here. At negative 1, I have 1/2. At 0, I have 1. At 1, I have 2. At 2, I'm at 4. And at 3, I'm at 8. And then I'm going to connect my points best I can to make the nice curve I can make. And I have y equals 2 to the x. Not too bad, right? Exponential graphs are actually pretty easy to graph. Again, pay attention to your scaling. So for y equals 1/2 to the x, my base here is going to be 1/2. Therefore, that makes this decay because it's less than 1. It's between 0 and 1. Anytime it's between 0 and 1, it's decay. So again, I'm going to go to my calculator and I'm going to put it into y equals and then make a chart. All right, so these are my points. So at negative 3, I have 8. So here's negative 3, and I have 8. And at negative 2, I have 4. Nope, I think I missed it. 3 should have been right here. I apologize. Negative 1 would be 2, 0 would be 1, 1 would be 1/2, and 2 would be 1/4. So again, just connect your points. And that's going to go on. It's not going to cross the x-axis. So y equals 1/2 to the x. Hopefully you can draw your lines a little less shaky than mine. All right, next page. Exponential modeling. So some real life quantities increase or decrease by a fixed % each year or some other time period. The amount y of such quantity after 2 years can be modeled by one of these equations. y equals a times 1 plus r to the t, or y equals a times 1 minus r to the t, where a is the initial amount and r is the percent increase or decrease written as a decimal. This is huge. Okay, great. R is written as a decimal. The quantity 1 plus r is the growth factor, and the quantity 1 minus r is the decay factor. So let's try an example. The value of a car y in thousands of dollars can be approximated by the model y equals 25 times 0.85 to the t, where the value of t is the number of years since the car was new. Tell whether the model represents exponential growth or decay. Identify the amount, the annual percentage rate increase or decrease in the value of the car, and C, estimate the value of the car when the car will be $8,000. So looking at this, I look right here. Oh, let me move my screen. That's my fault. So right here, at 0.85, since it's less than 1, it must be decay. So for part A, it would be decay. So this is exponential decay. It's because the base is 0.85, which is less than 1. B, identify the annual percentage rate increase or decrease in the value of the car. Well, in order to do this, we're going to do 1 minus 0.85 since it's decay, and we'll get 0.15. So as a percentage, because we're looking for a percentage rate, so as a percentage, that would be 15% decay. And we do this because this amount here, that 0.85, is the amount of the original value remaining. So in this case, that means that 85% of the value is still remaining of the car, 85% of the original. So for part C, it says estimate when the value of the car will be 8,000. This you got to do on your graphing calculator. There's two different ways to do this. You can, for either one, you need to put it into y equals. So for y1, put in the 25 times 0.85 to the t. And then in y2, put in the 8, because this is in thousands of years. So this would mean the car was initially $25,000, not $25. So we're going to put in y equals 8. And then you want to find their point of intersection. And when I do that, I'll get the point 7.011, comma 8. So this means after 7 years, the value of the car will be $8,000, or approximately. Say approximately $8,000. You can also put this in your calculator and use the table feature and search the table feature, and I'll do that on another problem. So example 3, the value of a car y in thousands of dollars can be approximated by the model y equals 25 times 0.9 to the t, where the value of t is the number of years since the car was new. Identify the annual percentage decrease of the value of the car, and then estimate the value of when the value of the car will be $8,000. So it's the same as the problem above, since we know it's decay already. For part A, we have to do 1 minus 0.9, which is equal to 0.1. So therefore, that's 10% decay, rate of decay. And then for part B and Y1, I'm going to fix what I have. I'm going to change that 0.85 to a 0.9. Change that to an X because on the calculator it'll be an X. Excuse me. And Y2 will still be 8. And when I do this, I would have the point 10.815, comma 8. So this happens sometime after 10 years, or during the 10th year, I should say. So, and after 11 years, the car will be worth $8,000. We can't say 10 years because at the start of 10 years, it doesn't happen. It's after the 10th year starts. So you want to round up no matter what. Even if it was 10.01, you'd still want to round up. Well, in this year it says after the one up above we have a 7 years. So I guess this one's closer to 11. It should be during the 10th year it happens. All right, let's look at the next example here. In 2000, the world population was about 6.09 billion people. During the next 13 years, the world population increased by about 1.18% each year. Write an exponential growth model giving the population Y in billions T years after 2000. Estimate the world population in 2005. Estimate the year when the world population was 7 billion. All right. So we have to use the formula. Y equals A times 1 plus RT. We know the initial amount is 6.09 billion people. And we also know the rate of growth is 1.18. So as a decimal, it's 0 or 0.0118. So my equation is then going to look like Y equals, for A, 6.09 times 1 plus 0.0018 to the T. So 0.609 times 1.0018 to the T. And it asks the population was in 2005. And since we're starting in 2000, so T equals 0 would be 2000. That means that T equaling 5 would be 2005. So if I substitute 5 in for T, I'll have Y equals 6.09 times 1.0018 to the fifth. And I'm just going to type that into my calculator. And when I do that, I'll get 6.46, and that would be billion people. So that's one way to do it. Sorry, that is one way. No, that's the way we're going to do that one. Sorry, I'm looking at the next part. So that was all part A. So part B, it says estimate when the world population was 7 billion. So we're going to go back to the calculator, and in Y1, put in the equation we created. So 6.09 times 1.0018 to the X. And in Y2, we want it to be 7 billion, so 7 is what we're looking for. And when I do that and I find the point of intersection, it would be 11.871, comma 7. Or use the table feature. the table feature, we have to start looking in the y column for something close to 7. So I put that into my calculator, and when I look at this, year 6, I have 6.53 billion. Year 7, I have 6.61 billion. 8, 6.68, 9, 6.78. Right, 9 was 6.768, sorry. And then 10 was 6.848, and then 11 is 6.9288. And finally, for year 12, we have 7.0106. So this happens sometime between the 11th and 12th years. And since we're talking about whole years, we're not talking about part of years, we have to say the 12th year. So the 12th year, so this would happen in the 11th year. So in 2012, population would be 7 billion. All right. That one more problem with this. Maybe. There it goes. We're going to assume everything is the same from up above, except this time we're doing 1.5%. So my equation for part A, I keep hitting the thing, sorry. For part A is y equals 6.09 times 1 plus, I should say, 0.015 to the t. So it's 6.09 times 1.015 to the t. And again, we want to estimate when it was population of 7 billion. So in y1, put 6.09 times 1.015 to the x, and in y2, put 7, and the point of intersection, so it's 9.3547, so that would be in the year 2010, the population would be 7 billion. All right. The amount y in grams of the radioactive isotope chromium-51 remaining after T days is y equals A times 0.5 to the T over 28, where A is the initial amount of grams. What percent of the chromium-51 decays each day? So these problems are a little bit different because we don't have an initial amount and we don't really care about the initial amount because it's not going to change our rate of decay. So what we're going to do is rewrite our formula and break our exponent down into a fraction and a non-fraction. So A times 0.5 to the 1 over 28, and then we're going to raise that to the t power. So I'm separating out the numerator, the t, and I'm just writing the number that would be in front of the t, which is 128. Now in my calculator, I'm going to raise the 0.5 to the 1/28 power. So when I do that, I'll have A times 0.9755 to the t. So now I have to figure out what was my decay, because this is less than 1. So I'm going to do 1 minus 0.9755, and that'll give me 0.0245. Therefore, my daily rate of decay is 2.45%. I want you to try this one. All right, last page. Compound interest. Before we were working with simple interest. Now this is compound interest. Consider an initial principal, P, deposited into an account that pays interest at an annual rate R, expressed as a decimal, compounded n times per year. The amount A in the account 2 years is given by A equals P times 1 plus R over n to the nt. So I'm going to be using this formula. You deposit $9,000. That's P. My rate is going to be 0.0146. Find the balance after 2 years. So this is T, and it's compounded quarterly. Quarterly is 4 times a year. And that is N. So I have my formula. A equals P times 1 plus R over N to the T. So when I substitute in, I have 9,000 times 1 plus 0.0146 over 4 to the 4 times 3. So that's 9,000. And I'm going to put my decimal into my calculator. If I have a graphing calculator, I can type it in all at once. But if I don't, I'm going to have to break it down into steps. So 0.00365, and then 4 times 3 is 12. So 9,000 times 1.00365 to the 12. And that will give me $9,402.21. So my new balance after 3 years is $9,402.21. So that means that I only gained $402 in 3 years. All right. Oops. I want you to try this last one and then tell me the difference between the two values or answers. So how much money different was it? What's the difference between the two balances? All right.